Subtracted H here to get this product. Where else could we extract H's from? We could also extract H's from here. By the way, I didn't show resonance structure, but we could show resonance here. These electrons could just move here. That nitrogen does want electrons. We can move them here, and that would give lone pair on the nitrogen, positive charge there. That's a resonance structure, right? At this point, we can remove the hydrogen. What acid were we using in the mechanism here?
HCl.
HCl. We have a Cl minus. Cl minus. We take this H, put it in the double bond. We get this shown here, plus possible of stereoisomers. But we could also have the Cl minus. Take one of these H's, the electrons move in here, and we get enamine with the double bond at the terminal position. And these would be regioisomers, constitutional isomers. Double bond is in a different region. So yes to both of these questions. Abstracting the H and putting the pi bond in from a cation, what does that look like? What mechanism does that look like from organic 1? Aaron? What type of elimination involving a carbocation? E1. E1 is ionization to make carbocation, and then some weak base taking the H and putting in the pi bond. Some weak base taking the H, putting in the pi bond. At this point, if you show carbocation, it looks like the second step of an E1 elimination. You can always work from any resonance structure. I've said that before. Never let anybody tell you you can't work with this resonance structure. You can work with any resonance structure. If you want, you can have the chlorine take this, these move in, and then kick these over. Either way you want to do it. So I showed you that the carbocation there. All this happens because there's no H on the nitrogen to lose. And so you take an H from one of these here and put it in a pi bond, a carbon-carbon pi bond. No hydrogen to lose because we're dealing with a secondary amine. And so if we want to make water, we have one H there, oxygen, and we lose an H from either here or here for H2O, H2O. Enamine. Drugs. Sometimes you see drugs with enamines. Here's a drug for fibromyalgia. What do you see right here? That's enamine, right? Is it ene with an amine? Enamine. How would you make this enamine? What two compounds would you use to make this? What two reactants? The nitrogen and the carbon on. The carbon was originally what? Carbonyl. Enamine is an aldehyde ketone derivative. Carbonyl. Show the carbonyl, show the amine. Well, the amine would just be that. Diethylamine, and the carbonyl would be we'll just cut it off. The rest is cyclopropyl with all that over there. This reacts with that. minus H2O to give the enamine. How do you make enamines? Stuff like that should be quick. Secondary amine, aldehyde ketone. Secondary amine, aldehyde ketone. A little bit of memorization to get you going, but from there you met your mechanistic knowledge and all your miscellaneous understanding, such as this. Okay, there are lots of applications of amines and enamines. Mostly though amines. Amines, very versatile. You see them a lot. So there's a variety of ABC here. First thing, A is some special types of amines, known as hydrozones or oxenes. They're just special types of amines. By the way, in the lab report, when I used to be at Georgia State and the Organic 2 lab there was a big lab report. It was common that students would give a unique name to their lab report. The project there, I think it was 7 compounds that were made. I remember one title was, it was something about the 7 wonders of the world. Synthesis of the creation of the 7 wonders of the world. If you want to give your lab report some interesting title, go for it. I remember one was about a family. The analogous would be the fluorine was like the grandfather, and then these are the offspring. And in the introduction, they talked about how the fluorine and this other molecule gave rise to the nitrofluorine or something. What's a hydrazone? A hydrazone is a special type of amine. What is that right there? That's an amine. What's an amine? It's analogous to a carbonyl except it's the C double bond N. Amine, right? Well, if the amine nitrogen has a nitrogen on it, it's called a hydrazone. Just a special type of amine. Because NH2 is called hydrazine. If you're reacting with a ketone, the hydrazine reacts with the ketone to give the hydrazone. It's actually not a ketone anymore, but that is sort of the name of it. And this reacts here, and before you know it, you have lost water. The other amine doesn't react, and you just do your amine reaction and you make a hydrazone. So, that's nothing more than going back over here. And instead of doing NH2 methyl, you just change the methyl to NH2, you change the methyl to NH2, and it's the same thing we looked at before. It just has a unique name. Another one is if you make an amine, there's your amine. If your amine nitrogen has an O on it, particularly an OH, it's called an oxene. Mechanism we've already done. So those are 2 special types of amines, hydrazones and oxenes. They're fairly common types of functional groups. There's some drugs that have hydrazones, oxenes. I think the warm-up, there's actually 2 warm-ups, right? Yeah. The second warm-up, anybody know erythromycin? Probably most of you have taken it, or many of you. There are other types of macrolide. What does macrolide mean? Anybody heard of macrolide antibiotics? Macro means large. It basically means a large ring. That's this large ring, a large lactone. Esther here. Cyclic ester. Macrolide lactone. Antibiotics. This sort of discusses what we're looking at right now. Take a look at it. Hydroxylamine. So two special types. Another special type of amine is actually a special type of hydrazone. That's a hydrazone right there, yeah? Now if that nitrogen has a 2,4-dinitrophenyl, it's called a 2,4-dinitrophenyl hydrazone. We're getting bigger here. 2,4-dinitrophenyl derivative or hydrazone. 2,4-DNP derivative. What are these good for? They're good for something. This is a chemical test. Chemical test for aldehydes or ketones. You react an aldehyde or ketone with 2,4-DNP hydrazine, 2,4-dinitrophenyl hydrazine. That's hydrazine, 2,4-dinitrophenyl hydrazine. You will get the hydrazone, but this hydrazone is usually always a yellow-orange precipitate because of these nitros and the big phenyl. It only gives a precipitate, it only gives a product with aldehydes or ketones. With esters or amides, it doesn't give the precipitate because it doesn't give that chemistry. That's acid derivative chemistry. You don't make hydrazones from acid derivatives. You make them from aldehyde ketones. Now suppose I brought in a liquid, looks like water, colorless organics, okay? And I wanted you to tell me what type of compound it was. What's one of the first things you would do with that liquid? One of the first things I would do is probably run an IR, right? See what type of functional groups you have. Okay, the IR shows a carbonyl. So now you're saying, well, it maybe is an aldehyde, maybe it's a ketone. Could be an ester though, because lots of esters are liquids. How could you distinguish between ester and aldehyde or ketone? Right here. Treat it with this reagent, usually ethanol. What if you treat it and you immediately get an orange precipitate? That typically means you got this derivative, and thus it means you have what? You're known as a aldehyde or ketone. You rule out the ester. Esters do not give precipitate. Now there's other ways to rule out ester, but this is a chemical test approach. This proves, a precipitate proves it's aldehyde or ketone. Now, how do you distinguish between aldehyde or ketone? Tollens. Remember tollens? Tollens would then distinguish between aldehyde and ketone because only the aldehyde oxidizes the silver to silver mirror. Ketone does not. So a combination of DNP and then tollens would tell you, what if the DNP was positive, meaning you got a precipitate, and then the tollens was negative? That indicates you have a ketone. What other chemical tests have we seen? We have DNP, we have tollens. What else have we seen this semester? Collins? Really wasn't a chemical test. That was a transformation of alcohols, primary alcohol to aldehyde. The other one was Lucas. Type of alcohol you have. Tertiary reacts very fast, secondary slower, primary alcohol keep waiting. Have we seen any other chemical tests this semester? Seems like there was one other. Jones oxidation with the chromic acid, orange. Primary and secondary turn the orange to blue. Tertiary doesn't because tertiary can't be oxidized. Yeah. So there's 4 chemical tests we've seen. We may actually see another one. DNP, chemical test derivative. Lots of times you just make, a lot of times you have a liquid product, or a lot of times you just make a solid derivative so you can get a melting point. So sometimes people will say, hey, your aldehyde. Well, what's the melting point of the DNP derivative? Make the DNP get a melting point. Okay. C. A, B, C are all under what? Well, they're all kind of under imines. I don't know if I got a... I reckon we're under 2. 2A, 2B, and 2 is imines and enamines. Most of these are imine applications. C, Wolff-Kishner reduction. Have we seen that before? During test 2, Wolff-Kishner was to take a ketone, remove the oxygen, and have the CH2. We did Friedel-Crafts, make the acyl, then we removed the oxygen to get the alkyl. Remember that 2-step sequence? We had 3 ways to do it. Clemenson reduction, which was zinc, mercury, and HCl. Hydrogenation, you could also do it. The 3rd way was Wolff-Kishner. We showed this. And we said later on we'll look at the mechanism. Well, guess what? Later on is here. Let's look at the mechanism for removing the oxygen. Okay? Essentially, the oxygen is replaced with 2 H's. Wolff-Kishner. That's right, Mr. Wolff. I don't know where that's from. I'll give you 10 points on the next test if you tell me where that's from.
Really? Oh, wait, right now.
Too bad.
Huh?
I said, can we Google?
Too bad. Too late. You had a chance. I was just kidding. No points. Don't get mad at me. Okay. Well, how do you do this? Magic? Well, guess what the first step is? The first step is to make what? What are we under? We're under 2 something, 2C. What's the first step? First step is to refer to A, probably. What do we make up there with hydrazine? Hydrazone. The first step is just to make the hydrazone. Loss of water, right? Now usually when you make amines you use an acid catalyst. It's not absolutely necessary. It's very traditional, textbook-wise. There's no acid catalyst here. So you got to do this without the acid catalyst. You should be able to do that. Okay? Make the hydrazone. Everybody with me? Yeah? Now, how do we get from hydrazone to this? By the way, what else is formed here? Because that's important to help us with mechanism. Going from here to here, we form water, yeah. Ultimately, there's water formed. We've already formed the water. You're right. What else is formed? Into. How'd you know that? Just sort of look at the atoms. You got to have 2 H's here. N2. It is. N2. And that's a gas. Nitrogen gas. Triple bond. Right? Question?
Is there supposed to be another carbon on the hydrogen?
Why would there be another carbon on the hydrazone?
Like,
Oh, here. Sorry. Yes. Yes. N2. Okay. I don't know what the first person to do this reaction, I don't know what they were trying to make. Maybe they were just trying to make the hydrazone, and they put in KOH, and they heated it a little bit too hot. They got the fire too hot. They went to lunch, and so it heated too long. I don't know what happened. But at the end, they got this. Can you imagine the first time that was done? And the amazement of what happened to my oxygen, what happened to my hydrazone? How did I get this? Well, then they started to investigate. One of the first things they found out was it also formed nitrogen gas. Okay? Then mechanistic theory comes in, okay? Maybe somebody isolated the hydrazone here. Well, that makes sense because those two react to give this. KOH is important. If you leave it out, you don't get that. What does KOH do to this? What does hydroxide do to this to get this? How do we go from here? Well, hydroxide. Hydroxide is a what? Base. Also a nucleophile, right? But acid-base reactions are instantaneous. Anytime an acid-base reaction could happen, you should probably first do that. Just like go back to carboxylic acid chemistry. You got a carboxylic acid, or an imine, not an imine, but an imine, acid-base chemistry. First step is this just takes an H, leaves us behind. And we get, I'm just going to call this aryl, double bond N, there's one H left, that's a minus charge now, plus water. What do you want to do next? The next thing is something you should always do when you have a carbocation or anion, or at least consider. What should you always consider when you have a carbocation or anion? It starts with resonance. What is it? Resonance. Yes. Can you do resonance here? When you do resonance with an anion, what do? Do you move electrons towards it or away from it? Away from it. Organic 1, right? Where do you want to move them to? Electrons here, and move pi bond out, in, out. What does that give? Resonance arrow. Aryl, N, double bond to N, with one lone pair and an H. What's now on this carbon? Well, what does that arrow mean? Pi bond moving out to carbon to give lone pair. And that's a minus. Because all resonance structures have the same net charge, basically you need to look back at your resonance handout, right? From organic 1. Everything I've said for the last minute is written on that handout. Okay? What do you want to do now?
H plus transfer?
It is essentially an H plus transfer, but it's not internal, and so that terminology is not usually used unless it's internal. You want to transfer an H plus to here. Where do you want to get it from? Water. So yes, it is an H plus transfer, but again, it's acid-base reaction. What are we trying to accomplish here? Are we trying to get H's on that carbon? Are we also trying to get triple bonds between the nitrogen? What did resonance do for us? We now have double bond between nitrogens. Now we have a carbanion that can take an H. I'll try to move here, but not too far. So now we have an H there. Neutral molecule plus what? Hydroxide. Have we done anything amazingly radical? Be careful about saying radical. We're definitely not doing radical reaction. Anything amazingly odd here? We took a proton off, we did resonance, we put it back on somewhere else. What you want to do next? You basically repeat the process. Except that one step is not going to be called resonance because we're going to break the sigma bond. Hydroxide takes the H. Let me move over here. And we get aryl. H there. N, double bond N. Now we have minus again on nitrogen plus water. I'll have to come over here. What do you want to do now? Make pi bond, kick this off. Now this is not resonance because we're breaking this sigma bond. But that's going to give what? N, triple bond N, and then we get aryl H and minus. That's that. We could almost say anytime you make a pi bond kick off a leaving group, that's easy to do. How is this a leaving group here? We've said you can't just kick off plain carbons and stuff. It's a pretty plain carbon. I mean, this does not have to be aromatic. This could be just all plain alkyl. That's why the Wolff-Kishner does require pretty high heat. And maybe on the original handout from the aromatics, maybe it said 300 degrees. Wolff-Kishner initially required very high heat, mainly because of this step right here, expelling that off. What do we have going for us? One molecule converting to two. That's entropy driven. What do we need to do to get final product? This takes an H from water. We get final product plus what? Hydroxide. So we have hydroxide at the end. That means hydroxide is defined as what? Hydroxide is actually a catalyst. Because it's there at the end. It was not consumed. After seeing this mechanism, is it pretty darn simple? Or I should say this, a lot simpler than you thought it might be. Right here it looks like magic. How the heck did you lose the oxygen? Hopefully it's a lot simpler than you might have thought. What's the key intermediate though? Amine. Hydrazone, special type of amine. Questions about the Wolff-Kishner? Wolff-Kishner reduction. Apparently two guys named Wolff and Kishner got together and figured this out and probably published a paper. Lots of people read it and started doing the reaction. And then it made it into a textbook. Why? Because it's a very important transformation to remove that oxygen. D. Amino acids. It's likely you'll see this in biochemistry. Hopefully when you get there you will have a little knowledge about it. It won't be so brand new. We'll be able to focus on the details that you need to in biochemistry. Take an aldehyde ketone, usually aldehydes, because usually amino acids have an H on the carbon. React them with KCN, some type of cyanide source. Really some type of ammonia source, but you can use ammonium chloride. Because ammonia is a gas, but ammonium chloride is a solid, much easier to handle. Really, you just need HCN. But that's also a gas, and we talked about how that's difficult to use. Basically, you need a cyanide source and you need an H plus source. Ammonium chloride can be an H plus source. Some of you used ammonium chloride when you did your nitro reduction in lab. Is that right? Come in. So you use ammonium chloride? Let me first get this. Well, this sets up a complex equilibrium. It's not complex, it sets up an equilibrium. You got Cn minus, you got an H plus source. These can react in equilibrium to form HCN plus ammonia plus what else? We want to show this just alternatives. KCl. Now, which side's favored? Well, that's an acid. That's an acid. You got to know pKa's. I bet that's more acidic. That's probably the favored side. But there's probably some of this in equilibrium, okay? Because they're weak acids and weak bases. So basically, there is some ammonia that can be sort of free. And if you have ammonia and add on a ketone, what do you get? What do you mean NH2? You get the amine, right? Minus water. I've already seen that. Refer back 2 pages ago. Amine. Now, how can we get this here from the amine? What do we need to add to it? Greg? Cyanide. Could add here, just like a carbonyl, electrons up. What does that get? And then this needs to pick up an H. Where do you want to get the H from? Well, there's an H plus somewhere. I mean, with the ACN, we could have protonated that first. And then added the CN, we would have gotten that directly. All this is equilibrium. I mean, there's a, if you want to show this ionic, you can show it like this. But if you're going to show it ionic, I'd probably protonate that first. And there you go. If that was an OH, what would this be called? What somebody said? Cyanohydrin. And if you just react this with HCN, you get a cyanohydrin. But if you first make the amine and then react it with HCN, you get this structure. And I don't really have a name listed for this. It's not common. I can't even name it. It's not an M now. That's okay. No name for this. But if you take this and hydrolyze it, aqueous acid, what do you get? Well, that's an acid derivative. What happens to acid derivatives when you hydrolyze them? Hydrolyze it all the way back to the carboxylic acid, and now what do you have? This is an alpha amino acid. That's an amino acid, with this being the R group. So this would be, start with some aldehyde, and whatever your R group is, you would have on your amino acid. Do it. So, what's your favorite amino acid? Glycine? Well, there it is right there. Glycine just has H. There's no substituent on glycine, right? And it's not chiral. So you like it because it's simple and not chiral. Okay. Keep it simple. Alicia, what's your favorite amino acid? I don't think I can draw tryptophan. What type of ring is in tryptophan? Endo. Endo ring, right? It's called endo. The benzene and the pyrrole fused together. Endo. Tryptophan is used to make what? Serotonin. Many other neurotransmitters. Tryptophan is a very important amino acid. Let's see. I don't even know if I can draw any. Serine. No, that's got an OH on it. What? We need to move on. Basically, your amino acids have different R groups, except for glycine, it just has an H. Whatever that is, that could come from an aldehyde. Phenyl with an aldehyde, whatever. How about leucine? There's one right there. There it is, just upside down. You see it? Just upside down. What aldehyde would you use to make leucine? Make that aldehyde right there. Because that carbon used to be an aldehyde. We go back. This used to be what? Before it was hydrolyzed? A cyano. And this used to be what before HCN added to it? This imine. And this used to be what before ammonia added to it? This. This reacts with ammonia to give this imine. There's an H there. Then HCN adds. You get this, and then you hydrolyze the cyano to a carboxylic acid. Okay, E. These are all imines, where you see imines as intermediates. E. E is a sequence called reductive amination. It's a great way to indirectly add alkyl groups to amines. Can I get an amine? If you react an aldehyde ketone with a primary amine, you get an imine. Here it is. Right? What can we do with imines? You can add HCN to them and get the thing up above that you didn't hydrolyze. What else can you do with imine? You could add any nucleophile to it. You can add a grignard to it. Just like the carbonyl. It's a lot like a carbonyl. Another thing we can do here is we can reduce this double bond. If we reduce the double bond of the imine, I just turned it sideways, but instead of C8, instead of C double bond N, we now have C single bond N. But we have to add an H to each. You can do this with just hydrogenation, just like an alkene. H2. We end up with H here and H here, so it's CH2NHR. CH2NHR. You can also do this with sodium borohydride or lithium aluminum hydride. I'll do it with this. This is source of what? H minus. This is polarized, like a carbonyl. Electrons add to this, electrons up. We get R, N, R there. Two lone pairs, that's a minus. There's now two H's here. One there originally, one new. This just picks up a proton. Maybe you did it with sodium borohydride and ethanol. If so, ethanol can serve as a proton source. And you get that product. Or you can just work it up with acid, some type of workup. But with sodium borohydride, you can often use an alcohol and it will serve as the proton source. So, this is just reduced. Call it alkylated amine. Because if we go back and focus on the amine, not that part, focus on this. This is a primary amine. It has one alkyl group. But now the amine has how many alkyl groups? Has the R, which is the original alkyl, but now it has this alkyl group, whatever that was. So this is now secondary amine, and we put an additional alkyl on the nitrogen. It's a great way to indirectly add alkyl groups to nitrogen. We didn't directly add it, but we indirectly did it by first making the amine and then reducing. It is a great way to add an alkyl group to an amine. Because actually, if you try to do it directly, you'll get polyalkylation. Remember that from Organic 1? Look at the handout. Polyalkylation. Because we might think we could take something like this and just do an SN2 and that would give us there directly. That would be a direct alkylation. The problem is this product will then react here again and you'll get another alkyl group on there. But in this sequence, you don't get another alkyl group added. Much higher yielding two-step process called what? Reductive amination. Now this term actually applies to sort of this portion. Because this portion gets aminated. And there's a reduction along the way. Essentially what is it though? You make an amine, then you reduce it to the amine. And you guys did this in lab, right? A lot of times this is all done in one reaction, one sequence, one flask. In lab, you isolated your amine, then you reacted it with what? Sodium borohydride. You used 1-propanol as the source because your amine is highly conjugated, it's a little bit reluctant to be reduced, but okay. Now, the question is, can you do this all combined? And you actually can, and it's kind of a one-pot, one-flask sequence. Very common, it's probably one of the top 10 reactions in organic chemistry of reductive amination. There's probably about 20 or 25 top 10 reactions. This is one of them. What do we have here? We have aldehyde ketone, or primary amine, and we have some reduction system. What does this look like to you? First off, these two react to give what? I like to draw in the H here. It looks like an aldehyde. I'll keep it with the H. Gives that right. There's your amine. You got to say this before you go to bed every night. Aldehydes, ketones react with primary means to get imine. Right? There's your imine. Mechanism, straightforward, loss of water. Now, what can this component now do? Nickel, platinum, palladium, your choice. Reduce this just like an alkene. What do you get? CH2, NH methyl. CH2, NH methyl. So in this sequence, this would not be isolated. Brackets mean it's not isolated, but it just kind of continues on. All combined. Yes. Very common to have just this combined sequence. We need to look below. Let me just kind of take you through it, the highlights. Can we combine this with sodium borohydride? No. Tell me why. Think about that. That does not work. But it will actually work with a new hydride source, sodium cyanoborohydride. This is less reactive hydride source. We'll talk about why. Why is that needed? Why does this not work? And then predict the products below. Please do those. The ones below are all reductive amination sequences. The sodium cyanoborohydride is just an alternative to hydrogen in reducing the imine. Show the products below, please. There's also a handout somewhere that shows the sequence. Okay, guys, see some of you this afternoon in lab.
Yeah, my daughter.